Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor in Department of Mechanical Engineering of JIS College of Engineering, Kollam. Today's lecture, we will discuss about that unit cell properties. So, in Module 1, we are in Module 1, and today's subtopic is that is unit cell properties. Learning outcome: to understand the importance of different properties of unit cell which influences the various properties during solidification or during various processing of metal. So first of all, we have to find that is average number of atoms per unit cell. So in cubic structure, the corner atoms are shared by 8 cells, face atoms shared by 2 cells, and atoms in the interior are shared by only 1 cell. So if we see a cubical structure, there are total 8 corners. So in 8 corners, there are maybe 8 atoms. There are faces in a cubical structure. There are total 6 faces. So it may place one atom in the face, or the atom may be placed in the interior of an unit cell if we consider. So the average number of atoms per unit cell as a whole, in general, it can be written that is in average equal to NC by 8, that is corner atom by 8, plus face atom by 2 and interior atom by 1. So in average, that is average number of atoms per cell. In C, total number of corner atoms in an unit cell. In F, total number of face atoms in an unit cell. And in I, center or interior atoms. So using this above equation, we can find average number of atoms per unit cell. As we know, for first case, that is simple cubic structure. So as we know that in a simple cubic structure, only the 8 corner atoms are there in a cubical cell. Although this simple cubic structure cannot be seen anywhere, for the references and to understand, this is first of all we need to be assumed. So in this structure, there are 8 atoms corresponding to 8 corners only. So therefore, in C equal to 8, and there is no face atom and interior atom, so that will be 0. Now using that, if we fit that one in the equation 1, so we find that the average number of atoms in a simple cubical structure, that will be 1. So effectively, in a cubical structure of simple cubical structure, the total number of atom in a present in a unit crystal or in a unit cell, that will be 1. Although there are 8 corner atoms are there, that equivalent to total 1 atom per unit cell. Now next is for an body centered cubic structure, that is BCC structure. So in this structure, we know that there are 8 corner atoms and 1 atoms at the interior, that is at the center of the unit cell. Therefore, the NC is equal to 8 and there is no face atom, that is 0, and interior atom equal to 1. So using the above equation, that is we get that in average equal to 2. So effectively here 2 atoms are present in a unit cell. So difference between simple cubic structure and body-centered cubic structure is that in a body-centered cubic structure, there are one interior atom present in the unit cell. So effective number of atom, that is average or average number of atom per unit cell, that will be 2. In a face-centered cubic structure, which is also known as in short, that is FCC, in this structure there are 8 corner atoms present and 6 atoms at the faces of face, and there is no interior atom present. The NC is equal to 8, and in F, that is face atom, so there are total 6 faces are there in a cubical structure. So in a face-centered cubic structure, that is, it has faces atom, face atoms are there. So NF is equal to 6, and here no interiorly no atoms are present like BCC structure. So again, using that equation, we know that is, so in average, that is average number of atoms per unit cell, that is equal to, we get 4. Next is average number of atoms we need to calculate in a hexagonal closed pack structure. So in an hexagonal structure, the corner atoms are shared by 6 cells. Face atoms are shared by adjacent 2 cells, and atoms in the interior are shared by only 1 cell. So in hexagonal closed pack structure or HCP structure is totally different from the cubical structure. So as we know, the figure of the hexagonal closed pack structure, that is, there are hexagonal faces in the top and bottom. So there are total 6 cells are present in a face, in a corner of a hexagonal face, and face atoms are also present in the in that faces, in the hexagonal faces. And if present, some interior atoms are on there. So here now equation becomes in average, that is average number of atoms per unit cell, it becomes NC by 6, that is total number of corner atom by 6, NF, that is total number of face atoms in a unit cell by 2, and NI equal to center or interior atoms. For HCP structure, that is hexagonal closed pack structure, there are 12 corner atoms are there, that is 6 at bottom face and 6 at top face. 2 atoms at the center and of the above 2 faces, and 3 atoms in the interior of the unit cell. So therefore, NC is equal to 12, NF is equal to 2, and NI is equal to 3. Now using that equation above, so we will get average number of atoms per unit cell, that is equal to 6. So next is, that is called coordination number. Coordination number or density of packing is the term of nearest equidistant neighboring atoms, surroundings, and atoms under consideration. In general, less the coordination number, less the packing factor. First of all, in a simple cubic structure, if we consider, each corner atom is surrounded by 6 other atoms, and hence the coordination number is 6 in this structure. In body-centered cubic, each corner atom is surrounded by 8 of other corner atom, and hence the coordination number is 8 in this structure. In closed pack structure such as HCP and FCC, the total number of equidistant neighbors are 12, irrespective of the method of stacking of the plane. Hence, the nearest equidistant neighboring atoms surrounding an atom, that is the coordination number is 2n. Now in ionic solids, the bonds are not directional and hence promotes more close packings of the structure. Here the coordination number, or it may be called ligancy, is the number of anions surrounding a central cation. The ligancy is a function of ion size and can be found out space-filling geometry where other conditions for stable configuration are satisfied. The possible value of ligancy and the range of radius of cation by radius of anion ratio for a stable configuration is given in this slide. So this table number one is table showing possible values of ligancy, that is coordination number in an ionic solids, and the ranges of Rc by Ra ratios for a stable configuration. So first of all, if ligancy is 2, that is coordination number 2 for an ionic solids, the ranges of Rc by Ra varies from 0 to 0.155, and the configuration will get that is linear. In case of ligancy 3, ranges of Rc by Ra found 0.11155 to varies from 0.225, and configuration found that is triangular. Ligancy 4, the ranges of Rc by Ra 0.2252 to 0.414, configuration in this case that is tetrahedral. Ligancy 6, that is Rc by Ra value varies from 0.414 to 0.732, and configuration varies octahedral. Ligancy 8, ranges of Rc by Ra value varies from 0.732 to 1, and here you find the configuration of cubical structure. In case of ligancy 12, the ranges of Rc by Ra that is equal to 1, and the configuration is FCC or either HCP structure. Here the note, that is ligancy 5, 7, 9, 10 and 11 do not satisfy the condition for a stable configuration for any value of the radius ratio, and hence they do not appear. Now in this case, small problems are there. That is problem number 1. The ionic radius of an anion is 2.11 Armstrong. Find the radius of smallest cation that can have stable 8-fold coordination with above anion. So the ranges of these Rc by Ra for a 8-fold coordination number we can found from the table, that is it varies from that is 0.732 to 1. Therefore, the radius of smallest cation can be calculated by, that is we are taking Rc by Ra is equal to 0.732. Now Ra is equal to 2.11 Armstrong and Rc by Ra is equal to 0.732. Therefore, Rc is equal to, you can find 1.545 Armstrong. Here the problem number 2. The chloride ion has a radius of 0.181 nanometer. Calculate the radius of smallest cation which can be coordinated with 8 neighboring chloride ions. So here the given data, that is Ra is equal to 0.181 nanometer, that is equal to 1 nanometer equal to 10 Armstrong, and ligancy is 8. For stable 8-fold coordination, the smallest radius of cation is given by, as you know from the table, Rc by Ra is equal to 0.732. Because in a 8-fold coordination, it varies from 0.732 to 1. So for an smallest radius of cation, so that will be 0.732 only. That is Ra by Rc by Ra ratio. So therefore, easily we can calculate from, that is Rc is equal to, that is 0.132 nanometer, that is 1.32 Armstrong. Now next is, that is atomic packing factor. It is defined such as the fractional amount of volume or space occupied by atoms in an unit cell is called atomic packing factor or atomic packing density or efficiency. So here APF, that is equal to volume of atoms in unit cell, volume of the total unit cell. So volume of atom occupies in the unit cell, that is we can find out that is average number of atoms per unit cell and volume of an individual atom, and divided by volume of the unit cell. So such that the atomic packing factor of some cubical and HCP structures are calculated, such as in below. In a simple cubic structure, as we can see the figure, the atoms are assumed to be placed in such a way that two different atoms are touch each other. If A is the lattice parameter of the simple cubic structure and R is the radius of the atom. So from the figure, it is clear that if two atoms are touches each other in either direction, so in an unit cell, that is R, radius of one atom is given by, that is A by 2, where A is the lattice parameter of an unit or simple cubical unit cell. So therefore the atomic packing factor can be calculated, that is average number of atoms per unit cell into volume of an atom and divided by volume of the total unit cell. So in the earlier discussion we have seen that the average number of atom per unit cell in a simple cubical structure, that is equal to 1. And in this case, here we assume that volume of an atom is, that is taken as an Hertz sphere, so it will be 4/3 pi r cube, and volume of unit cell equal to A cube. So now putting the R is equal to A by 2 in the equation, in replacing the A value. So if we calculate, therefore, so equal to 0.52, that is APF is equal to 0.52 we get. So that means in an unit cell, the effective occupancy of an atom, that is equal to 52%, and remaining portions are vacant. Now next is, that is a body-centered cubic structure. So in a body-centered cubic structure, the center atom touches the corner atom as shown in figure. So in a body-centered cubic structure, as we know, there are total 8 corner atoms and there are 1 interior atoms are there. So as we can see in this figure, now we see that the center atoms are touches all the corner atoms. So again, in this case, it is taken if A is the lattice parameter of the BCC structure and R is the radius of the atoms, it can be written as, that is, dF square from the figure is equal to dG square plus GF square. So this, in this BCC structure, as we can see in this figure, that the corner atoms are touches the center atoms, and we have drawn a tangent and divided that one, that is into R, 2R and R respectively. And now from this equation, that is, we know that dF is equal to the total corner length equal to dG square, that is the length of the dG plus GF square, that is the height. So GF is nothing but here A. Now again, the dG square from the geometry, the dG we can find out, or dG square we can find out, that is dC square plus CG square. And here dF is equal to 4R, as we can see from the figure. So therefore, we are replacing now the dG square part into the original one, that is dF square is equal to dC square CG square plus GF square. So dF square, as we know, that is 4R square. dC is equal to the lattice parameter of an cubical cell, that is equal to will be A. CG also same, that is the lattice parameter for a simple cubical for a cubical structure, and GF also, that is we know, that is for same, that is equal to A. So now the equation becomes, that is 4R square is equal to 3A square. So ultimately the R value, that is relation between radius and the lattice parameter A, equal to given by R equal to A into root over 3 by 4. So now the APF, or average packing factor, that is given by average number of atoms per unit cell into volume of an atom and divided by volume of the unit cell. So from the earlier discussion, we know that average number of atoms per unit cell in the case of BCC structure, that is equal to 2, and volume of an atom as it taken as a hard sphere, that is 4/3 pi R cube. So now we are replacing the R value here in terms of A root 3 by 4, and total volume of the unit cell for the cubical structure, that is constant, that is A cube. So here we find that in an BCC structure, that is average atomic packing factor is equal to 0.68. So it indicates that in a BCC type of structure, 68% of its unit cell is occupied by an atom, and remaining portions are remain vacant. So some of the metals having BCC structure at room temperature with their lattice parameter and atomic radius given. So metals having BCC structure at room temperature found, that is in case of iron, chromium, sodium, tungsten, vanadium, molybdenum, etc. And the lattice constant A measured in nanometer, that is for an iron it is given 0.287, and atomic radius R in nanometer given 0.124. Chromium lattice constant, that is 0.289, and atomic radius is given 0.125. For sodium, that is 0.429, and atomic radius is 0.186. Tungsten lattice constant is 0.316 nanometer, and atomic radius is R given, that is 0.137. In case of vanadium, lattice constant 0.304 lattice, and the atomic radius is given 0.13. Molybdenum, lattice constant is 0.315 and atomic radius is 0.136. So with this, we are likely to conclude this session, and these are the references and recommended books and notes one can find. Thank you for joining this session.